So while he's getting that ready, so we're the MLQC of time series data group. And so I guess introduce ourselves. Greg.
Tyanne, Divya.
No, bad Jupiter.
And
Yes.
one more member who had to leave, Jasmine.
Yeah. And so what we were working on was taking data from NOAA tide gauges and trying to see if we could both identify when the data was either good or bad, and then also if it was bad, could we potentially fill the data similar to what people did when they were filling data gaps.
Okay.
Yeah.
Yes, now it is ready.
Okay. So, for our data sources, what we had were data from 5 NOAA tide gauges in Portland. We have a nice map here. Portland, yes. Boston, Atlantic City, Cape May, and Lewis, Delaware. And for each of those stations, we had about I don't know, like 17 years of data, I think, total. And we ended up using we ended up limiting that. So it was about from 2001 to 2017. We ended up limiting that because a lot of the data early on in the time series was missing a lot of data. So we ended up limiting our initial scope from about 2007 to 2017. So about 10 years of data from each gauge.
Hey, Greg, how often do NOAA tide stations sample data?
Yeah, so the data is sampled. That's a great question. The data is sampled every 6 minutes. And so for every year, that's like, ends up being something like
a lot of data.
Yeah, like 90,000 data points or something like that. So it's a lot of data every year. So we have a fair amount of data. And so we ended up limiting our working sample to about 4 years because we just wanted enough so that we could just start prototyping something. And then we did a lot of data exploration to try to figure out what stations might be best to start with. And so we ended up starting with Lewis and Cape May.
Yes. Also, we should describe the data set.
Do you want to describe the data?
Yeah. In the data, there's 5 different measurements along with all indexed by time. It's along the primary sensor measurement, the standard deviation of the water level that sensor measures, the backup sensor measurement, verified, which is the data that's been manually QC'd using alternative QC methods, and prediction, which is not an actual prediction you would expect out of a machine learning model, but the predicted water level based on NOAA's statistical tide predictions for that location.
And so in this case, what we're QCing is the primary data, because that's the main source of water level information that we use.
And so there was a ton of data cleaning, because there would be this data is all stored initially in databases, and there would be database entry errors, and there would be repeat measurements at time intervals that weren't supposed to be there. So there was a lot of data cleaning that went on.
We got rid of all the points that we wanted everything every 6 minutes, but sometimes it would go every 3 minutes, but it was really just a duplicate data point. So we got rid of all of those, and we would get rid of everything that had nans in every single variable. So we just showed our 5 variables, the verified, the primary, and so forth. If they had nans all across, we just eliminated it from our data set.
Yeah. And so you don't see much of that code because we took all that code and stuck it into functions that we hid in a utils package, because otherwise you would have too much boring writing.
And so, so this plot, so we ended up focusing on Lewis and Cape May because they just seemed like they had greater quantities of data available to work with, not having missing data. But those even still had a lot of missing data. So the blue this is over the whole time period. Our x-axis isn't quite right, but so that from 2007 to 2017, so about 10 years of data. The blue lines are when the primary data was missing data, so there was no data there. The orange is when the backup instrument was missing data. So basically what we were doing is trying to find a time span where we had a pretty complete data set, because we didn't want to have to deal with like huge gaps in our data. So we ended up using 2012, right? 2012 through 2015, so 4 years. But as Kate mentioned, we still had a lot of gaps in there. And so originally we thought about doing like a time series type analysis to be able to, look at what should be QC'd out. Because of the gaps and because we were just running out of time, we decided just to take everything that was good and forgot that it's even a time series for the purpose of our analysis. So just used all the time points that we had good, available data, and then we QC'd for those time steps.
Yeah. And so in order for us to test how different machine learning models worked on our data set, in order for people to be able to work on those separately, we took the data sets we wanted to train and the features and everything, we stuck them in pickle files, and then that way people could run them on separate instances, and then we could come back and compare.
Yeah. So
y'all wondering what pickles are.
We try different methods, like including, because we're doing like more like a regression thing, so we tried random forest and the gradient boost, and also chaos for the neutral networking method. And because first thing, like we did the classification, we just find out which one is the bad data, which one's good data, and we use the networking to also do that, the classification. And also we because we have some missing data for time series data. So we're just trying to find an alternative to how about if we train a machine learning model good, then we can predict those data, those missing points. Then we can try to fix the data. Yeah.
And it's worth mentioning that we probably spent 90% of our time just getting the data ready. And so literally this morning was when we really got into the machine learning component. So, so I think that's a valuable lesson. Data prep takes most of the time, which I think a lot of you know. So,
yeah. All right. So, I'm gonna talk
oh yeah. Okay. So mostly because I wanted to try using a neural net, we went and used Keras for that. And just to show you how simple it is to set up a neural net using Keras, and that uses TensorFlow as its backend. So Keras is like a wrapper around TensorFlow to make it easy to create neural nets. And TensorFlow is kind of the Google created machine learning module or package in Python. And so you can see just in a couple lines of code how you can set up your neural net. And we used a pretty standard approach just based on others' recommendation in terms of trying to do a binary classification. So is the data good or not? And so you run that with one line of code after you create your model. And this plot is just showing you over time, over 10 epochs, how the accuracy changes for both the training set and the validation set. And in this case, we used 2 years for each, just for simplicity's sake. And you can see how the accuracies are really, really high. So it's like 99% for the training data, and the validation data gets up to like 98.5. So that's mostly because there's not many bad data points. So out of that whole data set, there's like maybe like 3% or a little over 3% is bad. And so it does a really good job at saying when data is good. But of course, you could just say it's always good and get 97% accuracy. So just something to keep in mind. That said, it is doing a pretty good job at identifying instances where we have bad data. And so this is just one snapshot in time where you can see pretty clearly see there was gaps in the data, and then there's some flatlining and just some funky data. And this is showing you the dark colors show the likelihood of, well, the colors show the likelihood of the data point being bad. So 0 would mean it thinks it's definitely good, and 1 or yellow would be it's definitely bad. And you can see in this case, it's identifying those data points pretty accurately where there's clearly some bad data. So I think the positive was that it's not getting things wrong. When it's good data, it seems to get that correct. And in the cases I looked at just bad data, and it was about 72% accurate when classifying just the bad data points, which isn't bad for like just throwing something together in a few minutes. So we're pretty happy with that.
You want to talk about the random forest?
Yes, and we will know like why it's 70 something, because we did like compare the primary data with the verified, the manually verified data, but we also by using the random forest we can know why it's 70 something. So this is data that that is showing the relationship between the bad data for the primary data and the verified data, which is the bad one. So this don't have good relationship between them. But then we used the good data to train the model, but we didn't use all the good data. We just used something that Penjo can take.
Yeah, so yeah, sorry, we ran out of time to make pretty figures, so it came down to screenshots of the output. But these are, yeah, you can talk about them.
Yeah. So the first plot was just showing you. So this is just the x-axis is showing you the primary data, and the y-axis is the verified data. So the QC, the manually QC data, and these are when we know they were bad. So when from the previous QC where they're marked as bad data points, and so not surprisingly, you don't see a very good correlation. And then this was showing with the training of the model when we had good data points, how the model compares to the QC verified data. And the model in this case was using the other data types other than the verified data as inputs. So it's using the backup, the sigma value, and the tide predictions as inputs. And then this shows the prediction. Compare these plots. This is using, which one is this one? The gradient boost.
Yeah.
So this is showing you how the model projects for those bad data points for when we didn't have that primary data. So when the primary data was bad, could we project what it should be given those other data points? And it compares pretty well to the observed, to the manually QC.
And from this figure, we can see why it's like still 70% something, because most of them is still correspond. It's following the trend. It's like following the trend very well. Just some of the outlier, which means these outliers are the one that making the accuracy very low.
No.
And this was the same approach, but with random forest.
Yeah.
So that's the model with the good data. So we expect the model to do well in those cases. And then this is when the data was bad. But you can see it's quite an improvement over just, the raw output. So I guess we're not really sure what's happening in the middle there. But those are, again, we don't have that much data to work with just on the first cut. So I think as we add in more data, I think we have potential to see a lot better performance and start tweaking a lot of the variables and things like that.
One of the challenges, the sensors they use are pretty good, so you don't have much bad data to actually train on.
Right.
Curses. Okay, I think we've eaten up our time.
All right. Any questions? Yeah, water level.
Using mostly the current state measurements, I'm wondering how that QC, and if if that inflation
Mm-hmm.
and also whether you can just get some more QC from situations
I mean, one of the interesting things is a number of us who in this group use and care about data quality coming out of repeat time series measurements. And so there's a series of standard algorithmic approaches that you can take. And it was interesting to try to take a different approach rather than those. See how it works.
But yeah, I mean, I think definitely the fact that we have, so we use tide predictions as one of the inputs. So that's like a great baseline that with other data types you're not going to have, right? So that really helps kind of ground everything, because those are reliable. They're always at they're not going to be bad ever.
Do you have any concern that doing this might take out storms or any super amount, like a storm might combine with king tide and take that out?
Sure. Yeah. Well, that's why I think the amount of training data you're going to want to use more training data to capture events like that. But the hope would be in those cases you have the backup sensor, which should capture the same large events as the primary. But then also what we didn't have time to include is near neighbors. So a lot of times we'll compare to other nearby stations, which we usually have. And so those should experience the same large events. So there's some ways to avoid that. But yeah, good question.
You mentioned title data is like already added so because you have so few bad data examples, right? If you just synthetically create some bad data,
Yeah, we talked about doing that. Yeah, that's a great idea. Yeah, we threw that idea around, and you messed around with that a little bit. We just didn't have time, but yeah, we could totally.
We can like if you like, Greg, he has a lot of experience on like watching doing the deal with the data, so he knows exactly like what types of error it could be, and we can try to use the machine learning thing to see if it can just like we manually put it in and see if it can figure that out. Yeah, that's good idea.
Also, which model, which algorithm gave you that result?
Well,
We did have time.
We did like we had like two. Yeah, we trying to like do the classification using the free method, but actually we just use Keras for the classification and use the other random forest and the gradient boost for like doing this. It's
the
like
filling part.
filling the getting the news.
Yeah, so we didn't even get to that yet, but
But we can do like comparison.
thank you.